Morning all. Okay, so for some of you this will be the second lesson we've done, for the others will be the first. So welcome. Feel free as we're going through, ask any questions in the comments box. Any suggestions, write it in there. We'll see how we go. What I thought I would do today is we're going to go back through the basics of waves. I know for some of you you've done this fairly recently. Morning Jude. For some of you, we've done this fairly recently. For some of you, it will be quite a long time ago. I know from some of the Year 11s, they struggled with some of the questions on this. Morning, Poppy. They struggled with some of the questions on this, particularly with ripple tanks. So we'll start from the basics. We'll go through. What I was then planning on doing is I'll put some questions on this into the Google Classroom for you to have a go at and then post the answers back. And on the next video I do, I'll go through some of the answers and any issues you've got. Morning, Mia. So, when we're looking at waves, we're looking at sort of any, I suppose, reciprocating sort of motion. Morning, Ben. So, we can look at water waves. We generally get students jokingly say Mexican waves, but actually that is a type of wave. We've got a motion that's going up, we're going down. We can separate waves into sort of two groups. So, we've got our longitudinal waves, and we've got our transverse. Now, one of the questions, let me just see if I've got this one on here. One of the questions that came up in the recent exam was this one. So, lots of students were putting down that actually it's an up and down motion. Morning, Drew. But they didn't get the marks for that one because the thing that was missing is it's 90 degrees to the direction of travel. So with this particular one, what we're looking at is we've got this idea that the direction of travel. Oh, hang on. Let's try that. There we go. I've got a button on this pen, and if you accidentally press it, it goes mad. There we go. Much better. Let's just shift this over slightly. There we go. Let's try that again. Okay. So we've got the direction of travel, which is in that direction. The movement is 90 degrees to the direction of travel. So to get the marks on the test paper, that was the two bits they needed. The just saying it's up and down we can pretty much get from the diagram, and it's also said in the question here, and we don't get any marks for repeating what's in the question. So those are the two bits that were needed on this one. So this is our transverse wave. Okay. The other type of wave we've got is a longitudinal. And again, I've got a diagram from this. All of these diagrams are taken from the exam papers, so they're all ones that you would get or have got at some point. Mike's a bit muffled. Is anyone else having the same issue? It's all on the camera, so I haven't changed anything since last time. Let me just make sure I've got nothing else using the camera for the moment. Let me just turn that off. And let's shut that down for a minute. Okay, I've just shut off everything else that might be using the mic, so we'll see if that works and we'll go from there. Morning Tara, morning Ollie. Okay, what I may look at doing is looking at seeing if I can get a better mic then, because like I said, at the moment I'm just using the one that's built into the webcam, but if we're going to be doing a few more of these over the next couple of, next several weeks, I'll buy a better mic for the future ones, okay? Okay, so, longitudinal wave. If you look at this one, we've got the oscillation here is in the direction of travel. So the direction at the moment is that way. Okay? So transverse, we're looking at 90 degrees to the direction of travel. When we're looking at longitudinal, we're looking at oscillating in the direction of the travel, and that's the key bits that's generally needed when we're looking at when we're looking at questions on this one. In terms of parts of a wave, then, let's just move this over. So let's just draw us just a simple wave. That's our transverse wave. Now, I'm going to put a line through, roughly through the middle. Now, let's go back to there, and let's go back to that one. Key things that we need to be able to annotate on this one. We need to be able to work out the wavelength. So the wavelength is the distance between the same 2 points on the wave. So we're going from that point to there, or we're going from that point to there. Now, you can take any other part of the wave, but generally speaking, you will make a mistake on this one. I've seen lots of people try and take it from midpoints on the waves, and they often don't get the same midpoints. There's mistakes in there. No, I don't think you are, Ollie. But like I said, we still need to collect some evidence in, and for some of you, you may want to look at doing the exams in September. So we'll carry on going as if. Hopefully, I will get a chance to see all of you guys in September anyway. I will definitely be going to the prom. We'll definitely catch up in one way or the other. But either way, we'll keep going. We'll keep the lessons going, and we'll try and keep some form of contact and learning going, if that's okay. Cool. So we've got our wavelength. And the symbol we use for wavelength, let's get rid of that, there we go. We use the Greek symbol lambda. So that's our wavelength. So, wavelengths measured in meters. The other one we need to do is we need to be able to put the amplitude down. So the amplitude is half the height. So we need to be able to make sure we can measure that on there. And again, it's quite a common mistake. A lot of people try and take the full distance, and it doesn't quite work that way. We've obviously got our wave in this case, because it's transverse, it's going to be moving in that direction. So we've got our direction of travel. And if we had a fixed point, so let's just say we've got somebody stood here counting, and they're sort of looking up, and they're counting. That's a really bad arrow. Let me just do that again. There we go. They're counting the number of waves going past. We would have the frequency. So the frequency is measured in hertz. Okay, and that's the number of waves per second. Okay. We can also calculate. Now, I'll go through how to use a ripple tank in a minute as well. We can either measure wave speed or we can calculate wave speed. The formula that we need is this one. And quite a few people didn't get this right. Although some people did get it right, but they got the rearrangement wrong. So we'll have a quick look at that in a moment. So we're looking at our velocity equals our wavelength times the frequency. So this is our wave speed. Because it's in a direction, it's a velocity, because the wave's moving in this direction. So putting v down for velocity is absolutely correct, because it's a vector, not scalar. And that would be in meters per second. Okay? So we could either, if it was something physical that we could see, like a water wave, we could actually measure the number of waves going past, we could work out the frequency, or we could put 2 points down if it was slow enough, and we could measure the time taken for a wave to move between those 2 points. Failing that, if we can work out the wavelength and we can work out the frequency, we can calculate using the wave equation. Now, just before I go on to the ripple tank, let me just bring up the diagram that I had a minute ago for the longitudinal. There we go. So with this one, we can actually still work out the wavelength, oscillating in the direction of movement. So our wavelength would be there. extra things that we can put on for a longitudinal wave is this area here is an area of compression, because the waves are quite close together. This area here is a bizarre word that I've never really used anywhere outside of science, and it's rarefaction. And that's an area of low pressure. If I'm working out the wave speed, generally I would say take it from an area of compression. It's usually easier to see where the middle of the wave is, to make sure that you get it from the same point each way. You can do it from the other one, but it's just that generally we get less mistakes this way. Right, let's just have a quick look at ripple tanks. Let's just move that there for a minute and let's bring a ripple tank in. So this diagram is exactly the same one as you guys would have had. Change colour just because I can. In the recent mocks. It was done quite poorly across the board actually, and I think it's possibly because in some cases the ripple tanks you've seen aren't particularly good. It's actually quite difficult to get a ripple tank working quite well, but the exam boards seem to like them. I'm sure there's better options out there, but you do need to have a decent one to actually see. So let's just go through the sort of things they're after. Now, the exam question itself was how can we calculate the wave speed, the frequency, and the wavelength. There weren't any marks for saying how this works. Now, there was enough answers in the question to show you how it works, and what we had was this idea of we had some form of motor, or there'd be something that's moving this wooden bar, and as the wooden bar is moving up and down, it's creating these ripples. So the light is shining through, and what we have on these is a clear plastic base which is showing the waves onto the bottom on this one. Now, if we can either calculate two of the features, so if we put our wave equation back up again, and again if I'm waffling or not making sense, do ask and I'll clarify. We can either work out two of these from the ripple tank, or we can work out all three, or we can work out two and we can calculate them. So in terms of the distance on the bottom of this one, I would be inclined to put a meter ruler down, or to put a ruler of some sort. What I would probably then do is, once I've got it then, is I'll take a picture with a camera. Because actually, if I had the picture with the camera, what we could then do is actually have a look at the distance between those two waves on the picture afterwards, and those distance aren't actually moving through. So that's probably the way I would do it. There are some ripple tanks where they will actually have a strain effect, and you can set the frequency of the strain effect to the same, and it looks like the waves are stationary. So again, we can still use a meter rule to work that out. The other option we can do, depending on the speed they're moving, is we could place a fixed point. So we could place something down here, and we can count the waves moving past that. So we can count the number of waves going past in 1 second. That's generally the hardest to do. The other option we can do is we could count the number of waves going past in 10 seconds, and then we could actually divide that down to calculate that way as well. If we had a meter rule down, or we had some distance, we could count the number of waves going past that, or the time it took for one wave to move down. That's generally the hardest one. What I would usually do is I would calculate the wavelength, I'd calculate the frequency, and I would actually use the calculation to work out the wave speed. From experience, it's the easiest way to do it. If I've waffled a bit there and that doesn't make sense, there's some really good YouTube videos, and I'll post the links up later on. I've shown these actually in use. I haven't actually got anything here that I could use to show you that one, but it's one that does make sense once you've seen the video on that one. But the marks in the exam were for explaining how to calculate these, not how to actually use the ripple tank, because that was given in the question. Hopefully that makes sense. Right, let's just move that over a little bit. Any questions on that before I move it on too much? Okay. So we've looked at waves. We've looked at the main sort of features of the waves. We just carry on going through. We can also need to have a look at how waves interact with objects. Cool. Cheers for the feedback, Drew. We need to have a look at how waves interact with objects. So some of the key words that we can have a look at then is we've got this idea of absorption. We've got this idea of transmission. That doesn't look right. I think I've spelled absorption wrong. Bear with me, I'll change that. And we've got reflection and refraction. Now, these are mostly to do with the electromagnetic spectrum, which I'll come on to in a minute. So I'm going to shift those up for the moment, and I'll come back to those when we do that bit. Most waves, though, can be reflected or refracted. And a lot of people were getting these wrong. So one of the questions, let me just put a couple of... let's do reflection first. Reflection should be the most obvious one. We're quite familiar with reflection, and if I was to draw a flat surface, and we can see this happening both with sound waves, with light waves, with water waves. If we were to have them colliding with an object, they're going to bounce off. Any of you that have sort of played snooker or pool should be even more familiar with this one. We know that actually if we shine, in fact I'm going to get rid of that for a minute, let's do an actual arrow. Let's do that. If we were to shine, still not there, let's try that. There we go. If we were to shine this in, much better. Sorry I'm being pedantic, but actually when we're doing exam questions on this, it's really important to make sure that we get continuity of where the light comes in and where it goes from, because actually we'll lose marks, and what the arrow was doing was going into the mirror then, which isn't technically correct. So I wanted to make sure it only hits the surface on this one. So we're shining some light in. So the other thing that we need to be able to draw on this one, I don't think I can actually do dotted lines, unfortunately. So I'm going to have to do... Yeah, no, I can't do a dotted line. That's a shame. So I'm going to draw a line on here, and I'll do it in a different colour so I can label it. This would be the normal line, and this should be 90 degrees. So this is our normal. And this is going to be 90 degrees to the surface of the mirror. Now, what we've got is when the light's coming in, we've got an angle here. Okay? And that angle is the angle of incidence. What we should have is when the light reflects back out again, let's do another arrow. What we should end up with is the angle of reflection, which is this one, should be the same. So that's the angle of reflection, that's the angle of incidence, and those two should equal each other. So if we look at a quick exam question that I've got here, this is one of the lower level ones. It's that one. There we go. We can see we've got the angles down here. We've got the angle of incidence going in, we've got the angle of reflection. The angles... Cool. So guys, what we'll have to do, because... let's do that. Bear with me. Remove. Report. Bear with me, I'm just dealing with... Cool. There we go. that was. They've gone. Let's carry on. Yeah, so what we've got down here then is we've got the angle of incidence coming in, we've got the angle of reflection, and they should be the same. We would generally get some amount of error, I suppose. A couple of things. One, it's actually really difficult, unless you've got a really, really thin beam of ray of light, it's really difficult to actually get the angles properly. So there's always some degree of experimental error. When we're actually trying to mark these up, it's quite difficult to actually draw down the line, so again there's some errors in there. So we generally get some degree of error, which is exactly what you've got down here. We can see that we've got some of these which are actually pretty good. And then we've got other ones here which are actually not particularly brilliant at all. So those ones we're going to have the biggest sort of source of error. Okay, refraction. Let's bring that in. There we go. Oh, it's the same one. Got a better one, so I'm trying to find the other picture. Where's the other one I've done? That one. Right. So the one we've got here, so the second one I've just put down, that was the one that came up in the sort of most recent mock exams. Okay? This is very similar, and they're answered in exactly the same way. This was light. And this is water. But it makes no difference on how you actually answer it. They're answered in exactly the same way. So what we're looking at doing is as the wave is coming in, as it's changing surface, so in this case we're going from glass, in this case we're going into shallow water, the first thing that's happening is it's slowing down. Now we only get refraction when the wave itself is coming in at an angle. If it's coming in at 90 degrees, the whole of the wave slows down at the same point. But when we come in at an angle, what you notice is this part of the wave is slowing down before this part of the wave. So because of that, this part of the wave at the top here is still going faster, and that's causing it to change direction. So because it's slowing down, and we're looking at part of the wave, we end up with this direction change. Okay? So part of the wave slows down, it's the part that's closest to it. As it enters the block, it changes direction, and then when all of the light, or when all of the water wave is in that sort of that different section, it's changed direction and it's now travelling through in a straight line. When it leaves it again, we actually end up with the opposite happening. So if you can imagine now we're going in the opposite direction, what we actually end up with is part of the wave leaving before the other one, and that speeds up, and that causes it to change direction again. So here what we would do is our wave, as it leaves, would do that. Okay, and if we were to have our normal line, then actually the angles would be the same. Okay, so we've got our normal line here, and we'd have a normal line here. So we've got our refraction. Okay. Okay, let's go over here and we'll have a look at absorption and transmission. So I'll leave that in the bottom corner. So, electromagnetic spectrum. So the EMS is always transverse. Okay, so we're always looking at transverse waves, so it's always going to be 90 degrees in the direction of travel. What we're looking at in this is a group of waves, and we're going radio, and you do need to know these radio waves. We're looking at microwaves, we're looking at infrared, visible light, ultraviolet, X-rays, and gamma. And if you watch the last video we did, we should be fairly familiar with gamma. X-rays, we have some fairly similar properties, but we'll talk about those in a minute. Up here, what we're looking at is a very long wavelength going down to a very short wavelength. Okay, so when we're looking at radio waves, generally we're looking at something in the region of, well, anywhere from hundreds to thousands of meters, so we could be looking at a couple of kilometers for one wave. When we go down to gamma, what we're actually looking at is something that's very, 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 very short. Now, the waves themselves are the same. If we were to have the same sort of intensity, the same amplitude with them, what we're looking at is one wave has the same amount of energy. Infrared. So if you think about how the remote controls on most TVs, some of the heaters that heats up muscles, infrared is that. And obviously UV is ultraviolet, and most commonly we get ultraviolet from the sun. We can also use it for security, and I'll come on to some of the uses in a bit. So what we're looking at is one complete wave is the same energy for all of them. So if we were to have somebody sort of stood, change off arrows, there we go. Again, technical diagrams, should be used to those with me now. If we're actually having a look at a radio wave, what we might be having is the wave is so long that we only get a fraction of the wave going through us in any one moment in time. But as we actually start working our way down the sort of EMS spectrum, the wavelengths become very, very short. So in actual fact, at this point, we could actually have hundreds of thousands of waves in the case of gamma going through us at any one moment in time. So the energy goes up. So when we start looking at some of the damage that gamma does, it's because we've got so many waves going through at any one moment in time. But the energy for one wave is still the same. Okay, if that makes sort of sense. The other thing we can have a look at here is when we're looking at visible light, we've got our rainbow. And what you'll notice is the red end of the spectrum is near infrared, the violet end of the spectrum is near the ultraviolet. Now, what I will look at is I'm going to do another section as well for particularly the year 10s doing triple later on, and we'll have a look at redshift. I'm going to have a look at a little bit more on sort of convex and concave lenses, and this becomes a little bit more important then. But when we're trying to look at and remember the sort of sequence of these, most of you know the order of the rainbow. We know the Roy G. Biv. It's something that gets covered in primary school. So if we know that the infrared goes with red and the ultraviolet goes with violet, we only actually have four of these left to remember. So the radio, the micro, and the X-rays and the gamma. If we know that the ultraviolet, yeah, there's a lot more energy going through us with a gamma dream because we've got more waves. It's not because the waves themselves have more energy, although we can increase the intensity. It's because we have so many more waves going through us at any moment in time than radio. I mean, if you think about it, we're swamped with radio. If we're sat in our homes and we turn the radio on, we're going to pick up a signal. So we've got radio waves going through us all the time, and we have small amounts of gamma from sort of cosmic radiation. But the gamma is the one that does the most damage. We don't generally we're not harmed by radio because there's such low energy levels. Does that make sense? Okay, while we're doing that, what I want to do... No. Okay, let's carry on. Brilliant. Yeah, so long wavelength, short wavelength, working our way down. Now, let's just move this over a bit, and we'll write down here. Yeah, so it's not that actually the waves themselves are more damaging, it's just the fact that we have so many more of them going through us. You do need to be able to talk about the uses of them all as well, so, and the dangers. So if we're looking at radio, the main one's obviously communication. Now, we can have oscillations in electrical circuits producing radio waves, and that's exactly what happens in an antenna. What we do is we can actually overlay, if you think about the fact if we can have an alternating sort of signal and we can make something oscillate, that's actually going to produce a radio wave. In the same way that sound waves, when they hit a microphone, those sound waves, so those vibrating sound particles, and we haven't really covered sound yet, but those vibrating sound particles will make a membrane in the microwave vibrate, and on the end of that, that's going to generate an electrical current. And it's a similar thing with radio waves. So the radio waves themselves are produced by an electrical current oscillating. Now, when they get picked up by an antennae, they do exactly the opposite. The oscillations in the radio waves then will make an alternating current, which is then picked up by the computer or by the circuitry that we have. So the main thing we're looking at here is communications. If we go down and have a look at microwaves, again, the big use, apart from we know the fact about cooking, but the big use here is communications again. So I will put cooking, but that's only one very, very specific frequency. So in terms of cooking, we've got one frequency that's absorbed by water. And it's actually absorbed by the bonds in water, and it makes these sort of bonds vibrate, and it transfers energy by giving it kinetic energy. But it's only one frequency. The rest of the frequencies, as far as we're aware of, and we haven't got any other research sort of suggests otherwise, it's perfectly safe. So your mobile phones, for instance, will work on the microwave frequency. And if you would actually put, and I've tested this out in schools before, if you were to put your phone into a microwave, do not turn it on. I'm not suggesting cooking your phone, but just put it in and shut the door. What normally you see is actually your phone goes completely down to zero signal, because it's the microwaves ovens themselves are designed to shield microwaves from getting in and out to keep us safe. So you don't generally get a signal from it. But like I said, don't turn it on. That will destroy it quite catastrophically, and the microwave. So, but yeah, so we've got the side of communications, and it is working on the microwave frequencies for that. We then go down to infrared. Again, we can have communications on there. If you think about the fact that you can send signals, your remote controls to your television is actually sending signals to the television, so we've got a form of communication. So we can put remotes down there. We're also looking at fibre optics. So I'll talk about how these work in a moment. But with a fibre optic cable, if you think about most of the internet backbone is on fibre optic cables. Now, we've got signals that's bouncing all over the world. I'm not actually sure where the YouTube servers are that we're talking on at the moment, but it's high chance they're not in the UK. They could be pretty much anywhere. Now, we have entire bundles of fibre optic cables that physically connect the UK to America and to other countries as well. So you've got the transatlantic link, which is a massive bundle of cables that stretches from the UK right the way across the Atlantic to America, and a lot of the communications goes down that. So I mean, if that went down, we would actually lose a lot of the internet. Not completely, but it would slow it down until they could work out sort of ways of rerouting, until they could work out repairing it. And those fibre optic bundles are literally glass fibres. So a fibre optic cable, if you've never seen one before, is literally just a glass cable. If you've got any form of sort of surround sound links up, a lot of the time they're actually communicating the TV to the surround sound system with a glass cable. And it's quite bizarre because they don't have to be in a straight line, and this is what takes people a little bit of time to get their head around. They can be completely coiled up, and actually we can still send signals down those fibre optics, and it's usually by some form of infrared. But I'll talk about how that's transmitted in a minute. In terms of hazards then, the main hazard of this one is actually burning. so we can put that in a different colour there. So we're looking at burns. And actually, if you look at some of the heaters, so I don't know if anyone's been to sort of Cowshot, but they've got a massive aircraft hangar where they've got the climbing walls and they've got the ski slopes, and it's not possible to heat up the whole of the hangar because they're not allowed to insulate it due to regulations, because it's a historic building. So what they have is infrared heaters, which they heat you up because you can absorb the infrared rays without having to heat up the whole of the space around them. But obviously if we get too close to infrared, we get burns. If you look at how a lot of the night vision cameras that use sort of thermal sensing, they can pick up body heat, and that's usually what they're looking at in this case. They're looking at the infrared that's being given off. So all of you at the moment are giving out infrared. And if you were to look at you through a thermal camera, the infrared that you are giving off is greater than the surroundings, so you would look like you're glowing. But that's just because all warm objects give off some degree or some form of infrared. Cool. Visible light. No dangers. Main use is going to be communications again. Let's just shift this over here. So then we start looking at the ones that are a little bit more dangerous. So we've got ultraviolet, X-rays. Hang on, I can't type today. I can't write today. Let's get rid of that. There we go. And we've got gamma. So ultraviolet. Some of you who have been to tanning salons, they basically are in ultraviolet. We get a suntan by absorbing ultraviolet light from the sun. So some people just go and do it in an artificial way. We'll look at the dangers associated with that in a moment. Other ones is when we're looking at security. And we get some from the communication here, but when we're looking at security, some of those sort of pens that we can have, the ones that we can sort of write on things and you can't see, or the one they're looking at banknotes, a lot of that will be done by ultraviolet light. Right, let me just scroll down and make sure I've not missed anything. Some of the more efficient energy saving light bulbs will give off small amounts of ultraviolet light, so we can use those as well. So we're looking at security and we're looking at suntan. Now the problem with all of these, and I'm sort of pretty much going to blanket all of these, is the fact they can cause cancer. It's one of the reasons we spend a lot of time outside. We don't protect ourselves. We don't start using suntan lotion. We don't use ways of absorbing or blocking the ultraviolet. We can cause ionisation of the skin. So again, if you watched the video I did the other day when we looked at gamma, you'll see that actually that gamma radiation, one of the things it can do is cause ionisation. It can cause molecules to sort of break bits off, turn them into ions, and potentially cause mutations, which lead to cancer. So we're looking at mutations here. And that's the same with all of those. So if we look at X-rays, we know biggest uses in medical uses. So we're looking at trying to identify bone shadows. Bones will absorb X-rays, whereas the rest of them will pass through soft tissue. So what we actually end up having is a piece of pretty much photographic film. It used to be, it's now done on computers with light sensors. So in the same way that your cameras and your phones work, they can do it the same way for X-rays now. But it used to be on photographic film, and what you would have is X-rays would make the whole of the film go black, apart from the areas where it was blocked by bones, and that would stay white. So the whole of the film would start off white, and then the X-rays would develop it and change it black. Nowadays what we have is, again, we'll have a light sensor. That light sensor will, everything will show up white, and then it will pick up the X-rays as a form of EMS, and then we'll look for the bone shadows. And if you've got a fracture of some sort, the X-rays can fit through the fracture, so we can see where those fractures are. So we often use them in sort of bone shadows, medical imaging, and some treatment. Well, that's normally gamma. So we're looking at gamma. We're looking at medical treatment. So that's our radiotherapy. That's where we're shining multiple beams of gamma radiation through, designed to try and kill cells. So we're looking at killing those cells off, which are usually going to be carcinogenic, and sort of combine it with something else. We can also use it for sterilisation. and I don't mean people, I mean equipment. So if you've got medical equipment or you've got food that's completely wrapped, because gamma is non-contaminating, and again we looked at the difference between contaminating and irradiating, we can use gamma to irradiate, which will kill off any microbes, pathogens, anything that might either cause illness or might cause food to spoil. Cool. Hopefully that makes sense. Any questions on any of that bit for the moment? Okay. Well, there, you're there. Cool. Okay. I was talking about fibre optics a moment ago. So let's just have another quick look at the fibre optics and how they work, I suppose. We've got this thing called total internal reflection. Morning, Kane. We've got this idea called total internal reflection. Or TIR. Now, if we were to have, and I don't think I can do curves on this one, I can do straight lines. Okay, so if we were to have some form of the one we normally do in school, and you will hopefully remember this, is where we've got a block like that. So we normally use a plastic block, it can be glass, it can be a different material. And we know that the light slows down when it enters. So what we end up with is, if we were to shine light in at an angle here, let's just drop that back a little bit, there we go. The light's passing through here. More relax. So the light's passing through here. This would be 90 degrees. It's not seen very easily in this diagram at the moment, but the light would be shining here through at 90 degrees. When it gets to this back object, the back wall here, what you would normally end up seeing, we would expect it to refract. But actually, if this angle is greater than what we call a critical angle, and the critical angle you don't need to know, the critical angle is just greater, it is dependent on the material, but if it's greater than the critical angle, what we end up with is reflection rather than refraction. So if we were to have a less angle, and I'll just draw another diagram. Okay, if we were to shine in a light angle, what you would actually end up having is refraction in this case. But actually, as you change this angle outwards, we end up with reflection. And this is exactly what happens when we start looking in fibre optic cables. So if we were to have a piece of glass, and this is I've done quite big, generally we can fit hundreds and if not thousands of conversations through a piece of glass about the same thickness as one of your hairs. What we actually end up seeing, let's change the colour, is we can shine light in and it reflects all the way down the glass cable. Okay? Reflects all the way down the glass cable rather than actually leaving the glass cable. And that's how the fibre optics work. So again, most of you, especially if you've got a fibre connection, I mean, if you're lucky enough to have fibre into your house, you will actually have a glass cable, a very thin one, coming directly into your house. What most people do though, I haven't got it here, most people, what they'll do is they'll have fibre to the local exchange. So somewhere in your road you have a green box somewhere where all the transmissions come in, and you'll have a bundle of glass fibres coming into that, and then you'll have a copper cable going from there to your house. But yeah, most of the internet, most of the communications that we actually use are travelling down by this particular method. So we're looking at TIR. Cool. Have I missed any on that one? Right. Just a quick question, just because it comes up, and and it's quite a common mistake people make. Hopefully you can see that. It's a little bit small. Let me see if I can make it a little bit bigger. No. So this is a question that actually comes up on foundation and higher. We're not using the normal wave equations for this one. We're actually using something a bit simpler. So the equation I'd be using for this one they give us a speed of sound in water is 1600 meters per second, and they tell us that it takes 0.25 seconds. So if we were to rearrange that, if we did 1600 times 0.25, we're looking at 400 meters. If my calculations doing it in my head quite quickly is correct. However, that's not the final answer in this case, because actually what has to happen is the sound waves has to go from the submarine down to the floor, and then it's reflected back up again. So actually what we need to do is divide that by 2. Our distance is 200 meters. And lots of people, they correctly work out the 400 meters, but they don't realise that actually, that because the pulse has to travel to the floor and back again, it's actually going to be half that distance. Now, while we're talking about, while I'm talking about sound, come on, there we go. Sound is going to be longitudinal. So what we end up with is sound particles that are vibrating. Now, they're still travelling. So they can still travel, but to pass that sound on, they've got to collide with another particle. And when they collide, they can make those particles start vibrating as well. If they were transverse, they would be oscillating 90 degrees to the direction of travel, and they wouldn't be able to pass on those collisions to other particles. So they've got to be longitudinal. So we create a sound, our vocal cords vibrate, it causes any air in our system to vibrate as well. Those air particles, oxygen, whatever, nitrogen, whatever, they will travel out, they'll hit other particles, they'll make them vibrate, and so on. And what I'm actually going to do is I will do the eye and how the ear works, which is triple, but I'm going to do that in the next video, either tomorrow morning or I'll do it on Friday. Okay, so those particles will hit and they'll cause them to vibrate as well. Sound particles respond in exactly the same way that light does, and the fact that we can reflect, they can refract, and we can still have them affecting other particles as well. Okay, but the main thing is they're longitudinal. Now, in air, the speed of sound is around about 300 to 330 meters per second. Notice though, what it says up there is that in water, it's much faster. And in solids as well, it's also faster again. In terms of why this happens, if you think about the fact that particles must collide in order to transfer that sound on, when we're looking in water, the particles are already touching. So because those particles are touching, it's conducted, it's transmitted much faster from one particle to the next, because they don't have to physically move to the particle, they're already touching them. So actually the speed of sound in water is much faster than in air. If we're in space, there is no sound. It was the tagline of one of the films years ago, classic film Aliens, and I've been through this with a few of you. In space, no one can hear you scream, and that's because there's no air in space. So it's quite interesting when you watch a lot of the sci-fi films, and you can sort of hear all this sound going on. Actually, it would be completely silent. You wouldn't be able to hear lasers, you wouldn't be able to hear missiles, you wouldn't be able to hear engines, you wouldn't be able to hear anything else, because there aren't any particles in space, so you can't hear it. The only time you can hear it is when something would collide with you, your ship, or whatever else is happening out there. But obviously it would make quite a dull effect if you couldn't actually hear these things happening. You'd end up pretty much having a silent film. So they've got to try and put the effects in. Okay, give me just a couple of seconds. Let me just skim through and make sure I've not missed anything that I was going to go through today. Right, so we looked at the ripple tank. There is another practical where they're talking about, and let me just shift this over. Let's go down there. I will, again, as I did the other day, I'll export all this out and I'll give you a copy of all this. I'll put it in Google Classroom. Oh, good question, Ben. In terms of making soundproof rooms, what you generally want is something that's going to absorb those sounds and not reflect them. So if you can think about when you've been in places with very, very hard surfaces, the sound reflects and it bounces around. But if you look at rooms where they've sort of tried to muffle it and they're looking at sound studios, what they'll do is they'll cover the wall surfaces in a material where the particles will hit it and they will absorb that sound energy. The particles will vibrate, but they're not actually going to conduct or pass them on to other particles. So the sound hits it, because if you think about those sound particles have energy because they're vibrating, but when they hit that object, they might cause those particles to vibrate, but probably not very much, but the energy of that sound is absorbed, so it's not reflected and passed on to other particles. Does that make sense? You see it quite a lot when you go in places, sort of big cathedrals and churches where everything echoes. It's quite cool actually. One of the things my wife was doing when she was working with some primary school teachers, those little tiny wind-up boxes that make music, you can go into Winchester Cathedral and you can put them on the walls, and you can actually make the whole of the Winchester Cathedral echo with something that's really, really tiny, because it's full of hard surfaces, and actually the way they're designed as well, they will echo and transmit sound quite quickly. So, required practical. One of the ones that comes up, just move that over there we go, is actually trying to have a look at how different objects absorb infrared light. So we can actually look at how, so we've done this in school I think, where we've had different colour tins. So we might have one of them painted black, and we can look at matte black, and we can look at shiny black, and we can look at some of them painted white. And we can have some of them that are silver and reflective, and then what we'll do is we'll have the same amount of water in these, and then we can do one of two things. We can either start off with the water being quite hot, and we can put a thermometer in all of these, and we can measure the starting temperatures, and we can measure the end temperatures, and we can actually look at which ones cool down. Or the other thing that we can do is we can actually have some form of infrared lamp, or some form of any lamp really, that gives off heat, and we'll have them all exactly the same distance, and we can actually measure the temperature and how it increases. Now what we should find out is actually the black one, particularly matte black, is going to absorb most of the infrared radiation. It will also emit the most infrared radiation. So if we're heating it up, it's going to get the hottest. If it's cooling down, it's going to cool down at the fastest rate. And that's because black is a very good absorber of infrared radiation and of all light, really. If you're wearing lots of black clothing in the summer, you're going to get hotter much faster because of the amount of electromagnetic radiation that it's absorbing. White is a very poor emitter and absorber. One of the reasons we see the colour light is that when the light hits it, all of the light reflects back. So very little of it's absorbed at all. So in the same way, if we shine infrared at it, most of that's going to be sort of bounced back, or any form of light, and likewise it's not going to emit very much as well. So it's going to have a very big sort of temperature difference. Now if we did it in the way I've set it up, hang on a sec. Yeah, sorry Chloe. However, you can go back and you can watch the video. It will stay on the YouTube channel indefinitely. What I will do is shut down the chat, just so your names aren't on there live forever. so there won't be your names on there. But this video, if you want to go back and watch any of this, I will never get rid of it. It will stay on there, and I'm going to be looking at doing these fairly regularly, so keep an eye on your emails and that. Okay. So just quickly to finish off, what I would do on these ones is I would put a lid on it to avoid losing too much heat to the top. Okay, I'm going to finish there. Just for what I'm going to go on to next time, I'm going to put this down here partly for my notes as well. We're going to look at how we see light. So we're going to look at how we can see it, how we can do colours. I'm going to look at the structure of the eye and how that works, and that will actually have some effect that sort of links into biology as well. I want to go through some triple content, so I'm going to have a look at convex and concave lenses, and we'll look at the ray diagrams that goes with that. Let me just double check the spec and make sure I've not missed anything else out on this one. Black body radiation as well. And I'll probably do the structure of the ear. Okay, I'll probably do the structure of the ear as well. Although these two in particular is triple, but you might be interested in that one. The other thing I'm going to look at doing as well, I know that a lot of the year 10s are doing cells at the moment in terms of the work they've set. I know my class I'm going to be setting cells next as well. So I will also do, I'll cover this one, and I'm going to do cells as well. Remember, on Google Classroom, I'm going to post up some questions on this for you to have a go at, and if you want to email back some of the answers to those, I'll go through some of the answers at the start of the next session. Hopefully that's been of use. Like I said, I will stop the video in a few minutes. Your chat won't be live on YouTube, so if you've got any other comments that you want to make to me, put them in Google Classroom and I'll have a chat with you on there. Okay? Cool. Enjoy the rest of your day, and good to see you on there. Not a problem, Poppy. Have a good day. Take care.